Swayam Prabha. Digital India. Educated India.
Today our discussion is on interpretation of control chart. Here is a control chart. You see that there are few data points which are scattered, and we have the action limit shown by the orange colors, and also we have the warning limits. So action limit is 3 sigma limits. Actually, to be very accurate, it is 3.09, but we can say it is 3 sigma. Similarly, 2 sigma limit, actually it is 1.96, but we can say this is 2 sigma limit, because 1.96 is close to 2 and 3.09 is also close to 3. So it is easy to remember, and that's why we say it is 3 sigma limit and 2 sigma limits. And then some points that you see which are there, and if this is the way the data points are on the control chart, then how to interpret this chart? How do I analyze such charts? Now, out of these so many points, the black dots, all of them are lying within the warning limit. So we can say these points till now, from let us say day 1 to day, this is 2, 3, 4, 5, 6, 7, 8, 9, 10. Till 10 the points are within the warning limits, so the process is behaving well. On the 11th day, we find a point which has gone beyond the action limit. So that means the process has gone out of control on the 11th day. So a single point outside an action limit is a strong evidence, therefore, that the process has gone out of control. But from day 1 to day 10th, the process was under control, and therefore all the points are appearing randomly in between the warning limit, upper warning limit and lower warning limit, and upper action limit and lower action limit. Now comes 2 consecutive points falling between same action and warning limit. If such thing happens, then what would be our interpretation? Now let us see this particular graph now, where we find 2 points are lying between warning and action limit. Rest of the points are working fine. They are in between the warning limits. Now on this 10th and 11th day, I find that 2 points are going beyond warning limit, but they're below action limit. Now the reason for this is that if the process is under control, the probability of a point, that is a data point, in between action and warning limit is likely to be 0.0214. Probability that 2 successive points will appear in between warning and action limit is 0.0214. We also explain that why it is 0.0214. So the probability of 2 successive points falling between the same limits is going to be 0.0214 squared. 1 point falling is 0.0214. So 2 points falling successively is 0.0214 into 0.0214. This is the probability of 1 point, A point. probability of A point. But the next point is also be there in between these two limits. Is also again 0.0214. So two successive points falling is going to be 0.0214 into 0.0214, that is going to be 0.005, provided the samples are independently drawn. So this probability that two successive points falling in between action and warning limit is very, very rare. It is too small, 0.0005, and therefore it should be concluded that the process is out of control. It is highly unlikely that two successive points will fall in between upper action warning limit. Similarly, it will fall between lower warning or action limit. Anytime either falling there or falling here. It may fall here also. These probabilities are very, very low. So we should say that most likely, it is highly likely that the process has gone out of control, even though it is not crossed the action limit. Now this probability that why the value is probability is 0.00, what is the probability that a point will fall in between the action and warning limit? Now if I draw this Z normal, that the normal distribution curve for this suppose variable that we are for which we are making the control chart. Suppose the distribution of that is shown by this normal distribution graph. So the mean is here. And now in the Z scale, Z2 is here and Z3 is here. So any point falling between Z2 and Z3 means basically they are falling in this zone. So how much is this probability? That which we want to find out. So probability of Z greater than 3, this you will find from the standard normal distribution chart or chart that we have in most of the textbooks. This value will get 0.0014. Similarly, P probability that Z, that in terms of Z variable, the value lying beyond 2 is 0.0228. Therefore, Z lying between 2 and 3 is going to be how much? Is going to be difference between these two. One is Z greater than 3 means basically this area. This area is Z greater than 3. Z greater than 2 means starting from here to this side, the right hand side area. So if I subtract these two, only the area in between Z2 and 3, that's what we will get. And therefore the difference between these two will be the probability of the point lying between 2 and 3 in terms of Z variable. Alright. So and now that is how we calculated earlier, and therefore it is the probability of one point. So two successive point means you multiply these two. So that will give you that figure which was 0.0005. Because since this is very unlikely, that's why we say whenever such thing occurs, we should be careful about the process. We have to check and make sure that the process is brought back to the original level. Now rule, while two consecutive points fall between same action and warning limit, then how do we go about it in this case? As I said, if a point falls between action and warning limit. The moment one point, this is the first point which has fallen. Inspect another sample immediately. So you go for going for another. So the second sample falls outside the same warning limit. Now this is the second sample. This is my first sample. And this is my second sample. Second sample also has fallen. Take corrective actions. And then if the second sample falls within warning limit, the process is within control. But if I take the second sample and find that this point is not between warning and action limit, but this is somewhere here. Suppose this point is here. In that case, we will make the conclusion that the process is within control. So the moment I find one point going beyond warning limit, whether upper or lower, we should quickly take one more sample and again check what is the value of that, and then we'll see whether it is coming in between warning or action limit or not. If it is coming between warning limit and action limit, then my conclusion will be the process is out of control. However, if the point comes back in between warning limits, upper and lower, then we'll say the process is still under control. One point has gone above warning limit does not mean that the process has gone out of control. When 2 points goes, then only we'll say the process is out of control. That is how we should look at the data and make the right conclusions. Now, another technical term that we use for quality control is known as run. Now, what is run? Run may happen at times when a sequence of data points lie between the center line and one of the warning limits. Center line and one of the warning limits. See, in this case, you look at the data points. They are mostly lying between the center line and the warning limits. So, all these points you look the way they are falling in between. The center line is here. This is the center line. It is falling in between them. Such a sequence is always called run. So it could be on the upper side, it could be on the lower side also, any side. A run containing 9 points is equivalent to a single point outside action limit and thus indicate lack of control. If 9 points, as let us say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in this case, it is drawn here, at least 9 points or more are falling in between center line and warning limit, then you will say it is in a way out of control, because the average is going to shift now. The average, the center line is here. If the process remains under control, then we are supposed to see the points falling on both sides of the center line. And there should not be any pattern once they are placed on the control chart. If they fall on one side only, that basically means it is showing some kind of pattern that it is, the process has little shifted on the heavier side. See, if I am suppose spinning yarn of a particular count, that basically means now I have started spinning little coarser count. So that is what is may be happening. So this kind of situation will also warrant that we have to stop, or we have to make some corrective action on the process so that we start getting points on both sides of the central line. Interpretation of trend. Now sometimes we see that the points are falling in such a way, there's a clear-cut trend. Now one trend is shown in this diagram. You see the points are still within warning limit, but the points are falling in such a way, it is going from left hand side, it is at the lower values are located here, and it is going towards the higher values. And if I join them by a straight line, I can see that there is a increasing trend, upward or downward, both are possible. In such situation, it is imperative to check the process for assignable causes before a point eventually falls beyond any limit. Now, if the process shows this kind of pattern, it is expected that the moment we go beyond, if we go still for some more points, the next set of points likely to appear here, here, and then here. That is likely to happen because the trend shows this. That means the process is drifting towards the higher values, and we need to arrest this. So any trend of upward trend, or it could be a trend like this side also, that is also possible. Both way it indicates that the process is likely to go beyond control limits. So we need to take corrective actions. That is what is required. There is also a chance like something like this. You see here, there is some pattern in the data points. You can see, if I say draw them by some line, we'll see the exact pattern. Any non-random pattern may indicate that the process is not subjected to random sources of variation and needs to be investigated. See, whenever we collect data from the process or the product that comes out from the process, whatever it is, then some variation is always will be there. That is called random variations. It is not due to some assignable causes. Some randomness is there that we have discussed earlier. Due to many reasons, there is some variation is always expected, but that variation will be random in nature. So therefore, if I keep collecting data related to the yarn count, or you collect data related to thick place, thin place, or GSM of fabrics, we'll always find, as long as the randomness exists, that means no systematic variation, there is no source of additional systematic variation in the process, and the pattern of the data points is going to indicate this. The moment a pattern appears, that basically means that there is something happening other than the random nature of the process, which is influencing the parameters in which we are interested, and therefore a pattern is going to appear. So in such situations, we need to investigate what is the reason. Like, see, if I draw them by a line, I can see a wave-like pattern is developing here. Here also some kind of wave-like pattern is developing here. So these are the possibilities which are there. The process, it indicates the process is oscillating. So points are within the warning limit, but the randomness is not there. There is something is happening which is causing the process to oscillate. So these are the situations that can happen when you start plotting the data points, and any randomness that may appear when the data points are plotted on the on the control chart, we should try to take corrective actions, because a pattern or a run or points, 2 points falling consecutively between warning limit and action limit, all are basically an indication that the process has gone out of control, or it is likely to go out of control. So we have to take then corrective actions before we start generating too many faulty products, whether it is yarn, whether it is fabric or anything. No. Before we generate too many faulty products, we must arrest the generation. So we must take corrective actions on the process. That is how the quality control chart is to be interpreted. Now we learn control chart for defective items. See, many defective items are produced in the spinning industry, in the weaving industry, in the garment making industry also. Defective articles are produced. So articles chosen from a production line are classified as defective or non-defective. Two-way classification we can make. Some are defective, some are non-defective. Sometimes some defectives are repairable, so we classify them separately and we say that there is some possibility of to repair them. That is a different issue. Otherwise, we can have two categories: defective items and non-defective items. So in a garment industry, it could be badly sewn garments. So that becomes a defective garment. Or buttons missing. Button and buttonholes are not aligned. There could be some more different types of, there could be different reasons for which we can say this garment cannot go to the customer. We have to either repair it if it's repairable, or we may have to sell it as a seconds sometimes. Whatever decision is taken, management that is different. So people can do the defective also can be categorized in that way, that some defectives may be repaired, some defectives can be sold as seconds, some defectives we cannot sell it at all with our brand name, because our brand value is going to suffer. Anyway, so that's a different aspect, but from any production line we can have articles which can be classified into two groups: defectives and non-defectives. Even if we make, suppose, cones on a cone winding machine or cheese winding machine, some cones are defectives. So we can classify that out of so many cones that we produce, how many are defective. So that data also we can keep and say so many defective cones are being produced by this particular winding machine. A quality of current production is number of defectives in a sample. So the quality check of the production line is how many defectives are being produced. That is basically the check of quality. Now let's say theta indicates number of defective items in a sample of size n. Theta is indicating number of defective items. Now to apply control chart, we need to know the distribution of theta. Theta is number of defectives. When the process is in control, that is when it is subjected to random variation only. Because of random variation, there will be some variability will be there, and therefore some defective item may be produced, but that is not due to some assignable causes. Some unassignable causes, something has happened, and therefore some variation is always possible. So the distribution of theta, that is distribution of defective articles, is what we need to know. In this state, it will still produce some amount of defectives. Even though the process is under control, still it will produce some defective. Because whenever we put the control limits between 3 sigma, if you look at the normal distribution curve, the curve actually goes beyond 3 sigma. So there will be always some possibility of articles being produced which is going beyond plus minus 3 sigma. Even though the process may be under control, the mean is at the right place, still this is what is going to happen, because that is the statistical nature of the process. Suppose the proportion of defectives produced in such situation is PC. The proportion of defective is represented by PC. If the sample size is n, that is, and sample is drawn at random, so I am not biased in drawing samples. That is not that on the fixed time every day I will come and check. So the samples are drawn at random. The number of defectives in it will vary from sample to sample, and it will follow binomial distributions. So you have all learned binomial distribution, and this is a typical case of binomial distribution. Number of defectives in a sample of size n, or number of faults in a sample of size n, something like this. We always following binomial distributions. And if it is binomial distribution, the mean is going to be n into PC, and standard deviation is going to be this. This is from the basic formula of binomial distributions. So what is the mean of binomial distribution? If P is the proportion, it is going to be NP, and the standard deviation is NPQ. So Q in this case is 1 minus PC. So root over NPC into 1 minus PC is going to be the standard deviations. And for standard deviations, once we know, if the sample size is large, n is quite large, 30, 40, 50 like that, it can be approximated by normal distributions. Also, it can be proved that when the sample size is large, this can be the number of defective items will follow, can be approximated. Binomial distribution can be approximated by basically normal distributions. It will not make much of a difference. And therefore, when n is large, I can directly find out the control limits by writing action limit is mean plus, this is plus minus 3 sigma. So actual value is 3.09 and this is the sigma value. This whole thing root over NPC 1 minus PC is the sigma. Similarly, the warning limit is going to be mean plus minus 1.96 root over NPC to 1 minus PC. So they become my action limit and warning limit. So this is because my sigma for the normal distribution also, and this is the mean for the normal distribution also. It will be always, therefore action limit will be fired. It will be mean plus minus 3 sigma. Beyond that is the threshold value of the action limit, that is a likelihood that 99% of the items will fall between plus minus 3 sigma, and 95% of the items should fall between plus minus 2 sigma or 1.96 sigma. That is how we can make the control chart for defectives. Now making a QC chart. Actually, how, whenever you have to make a QC chart, if you start working in industry, then we have to make QC chart. So how do we make a QC chart? Now, in an example, a garment production line is checked every day for number of defects produced by the line. Number of defectives produced by the line. Random sample of 200 is taken from the line and the data is shown in the table. So number of defective garments is what is shown here. Day 1 to day 25. For consecutive 25 days, there's one particular line we have chosen, and we see how many defects are there in this line. Day-wise details are given. So number of items inspected will be how many? Every day we inspect how many? Every day we inspect 200. Out of 200, on the first day, 6 garments are having defects. So they are considered to be defective items. The next day, out of 200, 7 are basically having defects. So this is day-wise data. But every day we are checking 200 garments. So on 25 days, we will check total 5,000 garments. So estimated fraction defective is going to be how much? What are the total number of defective items? That is 177. So 177 divided by 5,000, that is 0.035, that is the proportion defective on an average. This is the proportion defective. So what is going to be my mu D, mean defectives, is NPC. N is 200 and the mean value of PC we have found out 0.035, and therefore this number is going to be 7. So the mean is 7. So we expect the mean to be lying at 7. But you can see that the actual values, they are sometimes 7, 13, 0, 4, 6, 5, like that. And what is going to be my standard deviations? We apply that formula NPC into 1 minus PC. So that will be 200 into 0.035 into 1 minus 0.035. And if you work it out, you will find the figure 2.59. That is the standard deviation. So the standard deviation and the mean value is based on binomial distributions. Now we will make the chart. With these two information with us, we will have to make the chart now. So before that, once we start to making a chart, we need to know where my action limit is and where my warning limits. These two limits, where do they exist? And therefore we find out the action limits mu d plus minus 3.09 sigma and warning limits mu d plus minus 1.96 sigma. If you do it, it is 7 plus minus 8. That means it could be 15 on the upper side and minus 1 on the lower side. Warning limit 7 plus minus 5.07. That means it is 12.07 on the upper side and 2.07 on the lower side. So the values of action limit, warning limit, and the mean, these are now known to us. So once it is known to us, we plot the chart. So the points here, we have joined them together. You may not join also. It's not that the joining has to be done. It's a choice. One can join, one may not join. Doesn't matter. So on the x-axis, we have days. We have started with day 1. We have gone up to day 25. And the warning limit and action limits we have plotted as per whatever we have found out. So these are UCL means upper control limit and upper warning limit. Similarly, LWL or LCL, we can write them. Now, if you look at the points, you see sometimes the points are going up. No, this is the point which has gone beyond action limit on particular day. The next day it has come back again. Another day this value has gone up beyond this. There's another day it has gone like this. Here also it is. This is gone beyond warning limit, but this and these two, the values are gone beyond action limit. So this is how we plot, and then what we should do, if we want to have a try to now interpret the results, 2 data points fall beyond upper action limit or upper control limit, whatever you say. So 2 points have gone beyond this thing, this it is necessary to find out for any assignable causes on those days. So the previous slide it was there. We have seen that the 2 points are going beyond the action limit, and that was sample number 14th and 20. That means on those 2 days we have to now find out what has gone wrong, and for that it is difficult to find out reasons in retrospect because those days have already gone. We have also taken samples after those days also. But what we can do from our records, if they are maintained meticulously, then one can check whether on those days operators were changed, or raw material was changed, or machine was changed, or the machine became defective, whatever it is. Something must have happened on those days. Therefore, it went beyond the action limit, and then again it has come back to the in between the warning in between the warning limits. So that means process went temporarily out, but again it has been brought back. So something must have happened on those days, so that those days one can check from their records what actually happened on those days. As I said, something we have written here that maybe operators were different. One operator did not come because he may be absent on that day, so he was replaced by another operator. And there may be a deficiency, that may be, the skill level may be different between the 2 operators, which can lead to more defective items to be produced. on a particular day. So something like this must have happened. So that sort of analysis one has to do, and one has to find out what is exactly the reason. So now, because on the 14th and 20th day, the defective garments are more in number, 18 and 17. So what we will do now, we will remove this data and then recalculate the warning limits and the action limits. For that, what we need to do, if we remove these two data points, then we have total 142 defective garments we produced on how many days? On 23 days. So it will be now 4600 total number of this produced, and estimated fraction of defective is going to be now 142 by 4600. That gives you a figure 0.031. Now the mu d, the new mu d or the revised mu d is going to be 6.2, and the revised standard deviation is going to be 2.45. So that is, these are the changes which is there. And now based on this mean and standard deviation, we go for revised action limits. So this is mu d plus minus 3.09 sigma. So that gives you two values, upper value 13.77 and lower value 1.37. Same thing we'll be doing for the warning limits also. This is mu d plus minus 1.96 sigma. So we put the values of mean and the sigma. This is the revised sigma, and therefore the new limits are coming now 11 and 1.4. So this is the change. Because of this change, we have to redraw. So let us look at the control chart again. See, dotted lines are showing you the redrawn lines. Earlier, UCL, the form lines are indicating the UCL and LCL values which were there earlier, but now because we are going for a revised values of warning limit and action limits, and they are shown by this hatched lines. So, and you can see that there is a change now. Some change has happened, and these are my new action limit and warning. So you can remove the original ones, all the farm lines we will remove from the chart, and wherever these dotted lines are shown, we'll take those dotted lines as the new limits of the control chart, action limit and warning limit. This is how we should revise. We are revising because of we are expecting that, because we have found out some reasons why it has gone beyond the action limit, and these reasons is a assignable reason. There is a specific reason why it has gone up, because as I said, maybe that particular day the operator was not so skilled, or maybe the operator was not, he had suffered something, probably he was weak because he was sick, or the machine sometime went wrong, or maybe the raw material was changed which was coming to him. Because all these reasons, if there are assignable causes, then we can always change the limits and we can go for new limits. That limit is going to be the limit for the random variations in the generation of defects. So some defects will be generated because of random nature of the process. There are many reasons for which it could be there. That is how the control charts are drawn, and we have to interpret them. So control chart, discussion is not yet over. We will learn more about them in the coming 2-3 more lectures on control charts. We have just learned the control chart of defective items. The items could be anything. So we'll have some more discussions on quality control charts. With this, we are closing today's session. Thanks. We meet again in the next class. Thank you.